orange stairway, and then we will have a reception and a drink and so on. Congratulate our new professors. But I will let Mads give the word to you. So
thank you, Hans. I suppose it's a sign of old age when you start wondering what it is you've been doing and why you were doing it and all those sorts of things. But that's what I intend to, well, those are the questions I would like to answer with my talk here today. My talk is entitled Statistical Parametric Speech Processing, Solving Problems with the Model-Based Approach. And well, my motivation for giving this talk here today is that looking back, there are certain ideas that permeate my research, so across many different collaborations, publications, and research projects and all that. And briefly put, those my research has revolved around two ideas or two principles. One is describing and analyzing audio signals using parametric and statistical models. And the other is posing and solving engineering problems in audio and acoustics using optimization, linear algebra, and statistics. So what I'd like to do here is tell you a bit more about those ideas and what can be achieved with them. And I'll do this in the context of speech processing, although you can apply these ideas to many, many different things. So here's an outline of my talk. I'll give a bit of, I'll give a bit of motivation first, introduction, and then I'll introduce you to the model that I'll devote the rest of the talk to, namely what we call the harmonic model. Then I'll talk a bit about how do you find parameters of models, what are the principles involved, can you say something about how well it's possible to find such parameters. Then I'll present three different methods, some of which we have invented. And then after that, I will address some specific problems using the model-based approach, namely how can you do multi-channel modeling? So how can you extend your basic model to multiple channels? And then I'll address the problem, how can you, based on this model, do noise reduction? And finally, how can you account for non-stationary speech in these models? And then finally, I'll discuss some applications and implications of research here. All right. So parametric speech models have been around for many, many years. And you can go back to the 70s, and people were really interested in predictive models back then, and the early speech coders were model-based. You had sinusoidal models in the 80s and all that. So that idea is certainly not new. And skeptics argue when you work on these models that the models are always wrong, and even if they were right, it would not be possible to find the parameters anyway. So those are some of the comments we often get from skeptics, often in the form of anonymous reviewers. And so we devote a large part of our effort to proving these guys wrong. But what we say is that even if these models are not perfect, then we can use them to a lot of different things, and do things that would otherwise be really, really hard. And the model I'll be talking about here today is the harmonic model, and that is a good model of quasi-periodic signals. And in this case, it would be voice speech, but it could also be music signals and many other kind of signals. And this model basically describes your signal in terms of pitch or fundamental frequency, a set of amplitudes and phases, and that's it. All right, a couple of quotes about models here. A famous one in statistics is that all models are wrong, but some of them are useful, by George Box. And I think we can also say that we have encountered this attitude here. And it's not that we disagree, we're not saying the models are perfect, we're just saying that they're useful. Another famous quote about related things is that everything should be made as simple as possible, but no simpler, which I think is also an important thing to keep in mind when doing modeling. We're trying to capture the essence of the problems, but we don't want to make the problems overly complicated. On the other hand, if you do something that's too simple, you'll get worthless results. And finally, a funny quotation here, which is that for every complex problem, there's an answer that is clear, simple, and wrong. And I think that's an important thing to remember also in engineering, because we're often looking for sometimes those very nice and neat, simple solutions to our very, very complicated problems. And of course, there's no guarantee that these simple solutions exist. Yeah. So the methodology of our research you could describe as being rooted in estimation theory. It's been based on parametric models of the signal interest, so in this case speech signal. And you could say that what we've done is that we have seen analysis of estimation and modeling problems as mathematical problems. So trying to be as mathematically rigorous about these things as we can be so we can understand the problems we're trying to solve and not just solve them. So why these parametric methods? Well, because they lead to robust and tractable methods whose properties can be analyzed and understood. In other words, we understand when they're supposed to work, and if they don't work, we have a pretty good idea what might have gone wrong. Also, I think it's worth emphasizing that with some of these models, you actually get a full parameterization of the signal interest. So even if you aren't interested in these particular parameters that we're using, you can find whatever you might be interested in from them. And something I argued, and this is often in the case of music processing, is that sometimes we need to go back to basics. And how can we hope to solve really complicated problems if we cannot solve even really simple ones? An example here is some of the attempts in the music information retrieval community at, let's say, do source separation on a piece of music played by a symphony orchestra. That is really, really complicated. And most people realize that even separating two speech signals from each other is really, really difficult, right? So if you cannot separate two speech signals, do you really think you can separate maybe 100 different instruments playing a symphony? All right. So some questions you might wonder if you make a method for analyzing speech audio signal. Could be something like this. Under which conditions can a method be expected to work? How does the performance depend on the acoustic environment? Do we have a good understanding of that? Is the method optimal, and what would that even mean? And finally, how do we improve the method if you think it's not good enough? And a point we've been making over and over here is that the only way we can answer these questions is if the assumptions we make are explicit. So people may say the assumptions are wrong and all that, yeah, but at least we're explicit about these assumptions so we can see if we can do something about it. And I'd also like to point out that often these assumptions are actually sufficient conditions and not necessary, which means that the results may hold for other cases as well. And I think that's a point that a lot of people forget. They say, well, this is not true, so the whole thing breaks down. That's not necessarily the case. And also, a lot of the non-parametric methods that people like to apply in speech and audio are what you could call non-parametric. And often you have a very bad understanding of what they actually do and what you should do about what they know. Okay, so the harmonic model looks like this. We have an observed signal here, which is comprised of two parts. S here, which is the voice speech, and E here, which is they call it observation noise, but it could actually also be stochastics part of this part of the speech. And the S part we model as a sum of complex exponential functions here that have frequencies that are integer multiples of a fundamental frequency, which is also what you call the pitch in speech audio signals. And each of these, what you call harmonics, have a complex amplitude here. And and then we have the noise. So S is the voice speech, E is the noise. Omega 0 is what we call fundamental frequency of pitch, and then the frequencies are L times omega 0. And we can stuff all the parameters that we might be looking for into this spatial parameter here. We can also write this in matrix vector notation, such that we define an X here with M samples in it. Like this here, we use it with S and E. And then we can describe the part that was that's S here as a matrix set here, whose columns are these set of omega vectors here. So these are basically complex exponential functions, one for each harmonic. Then we have a vector A here, which contains all the complex amplitudes. Then we have this D matrix here, which shifts these different frequencies when raised to the power n up here to account for the index here. And these different ways of writing these, why do I bother writing these? Because these are useful in different contexts. Sometimes it's useful to think of the set matrix being time varying. Other times it's useful to think of the amplitude as being time varying. So depending on that. Sometimes this model. If we compute the covariance matrix of X here, like this here, well, we can plug in our signal, and then we get a part here, which is the noise. We call that the noise correction called Q. And then we can see that this other part here, we get this set multiplied by P, and set information transpose here. And then this P here is the covariance matrix for the amplitude. Now, often in the methods I'll be talking about, we'll make the assumption that the noise is white. Now, that's of course something you can argue is that true, and what I do about it, provided it isn't. But this is often used, so in that case, Q is just a scale identity matrix. What about this P matrix here? Well, you can see here it's actually the covariance matrix for these complex amplitudes. And you can show under certain conditions here that this tends to be a diagonal matrix, such that where you get the sinusoidal amplitude raised to power 2, so essentially the powers of the different harmonics on the diagonal. And this is an example of what I mentioned before with the sufficient conditions, because this model actually came from array signal processing, and particularly for literature on narrowband array signal processing. And the assumptions they make there to end up with this model here, it's not exactly clear how this applies to something like time series analysis. But you can actually work this model out that even if you assume the signals are deterministic and you compute a sample covariance matrix, you end up with the same result. So that's another example of this sufficiency of these conditions. So what's wrong with this model? Well, anonymous reviewer number 1 might argue that it does not take non-stationary into account and speech is continuously varying. You might say, well, I don't think the background noise is right, and I don't think it's even Gaussian. You might say, well, the model order, so the number of harmonics here is unknown and it's time varying. And even if the signal was stationary, the signals are not perfectly periodic for unspecified reasons. And the model does not differentiate between background noise and non-noise speech, and it's single channel. In many cases, you only want multiple channels. And the basic question here is, of course, can you deal with this? Or another question you might ask, does this matter? And those are some of the things that we investigate. And those are some of the things I will also explore with the examples I will do later. So, how do we go about estimating parameters? Well, what does it even mean to estimate parameters, and what does it mean to have a good estimate of parameters? Well, we say that we have an estimate of theta I here. We put a hat on it when it's an estimate, and then that's an estimate of theta I here. And then you say that an estimate is unbiased if the expected value of the estimate is the true value. And any difference is what we call bias. Then there's something called the chromatic bound, which says that the variance of this estimate here is then always larger than or equal to, for any unbiased estimator, the inverse of this I matrix here, or the diagonal element corresponding to the I parameter here, of this Fisher information matrix, which involve the second order derivatives of the likelihood function. So you can actually say something about the extent to which you can find these parameters. And you can say something about how well you can estimate them. And for the harmonic model, you can arrive at these bounds here. So you can see, for example, you can put a bound on the variance of the fundamental frequency here. See, that depends on the noise variance. Well, this is called white Gaussian noise. So the variance of this white Gaussian noise here, it depends on the amplitude squared. It depends on how many harmonics you have and how many numbers you have here, amplitude squared. The amplitudes depend on the noise variance and how many samples you have. It's inversely proportional to n. Up here it's inversely proportional to Q. And you can also say something about the phase down. And they depend on, you see they depend on this weighted signal to noise ratio kind of thing here. And if you want to extend these results to color noise, so what you've got to do is you've got to apply pre-writing to the entire signal. So you change the noise, power spectral density such that it's white, and you change the amplitudes in the process also. And then you can apply the result here. These bounds are useful for a number of reasons. One is that if you can show that an estimator had changed the bound, well, then you know it's optimal. And you can stop searching for a better estimator. The bound also tells us how performance can be depend on different quantities. And we can, of course, also use the bounds as benchmarks in simulations, and they can give us rules of thumb for when we're trying to solve the problem. As an example, we could see from earlier here that higher harmonics are actually really important in determining the fundamental frequency. So if you have a lot of higher harmonics, you should actually use those and not discard them as is currently being done. One thing about this primary lower bound, or CRLB, is that it does not accurately predict the performance of nonlinear estimators under adverse conditions, what is called thresholding behavior. But it is also possible to compute what is known as exact primary lower bounds, where you don't make asymptotic approximations, which are some that I used before. And these actually do predict more complicated phenomena. Okay, we might also wonder, can we say something about it if we're trying to estimate parameters and then we want to use those parameters to actually re-synthesize signals with? Can we say something about the errors we make then? Well, actually we can. If we say that our signal is now, observed signal is X, and there's some noise E as before, and now we have S of theta here, and now we estimate theta and call that theta hat, and we reconstruct the ith sample here. Then you can, and say we make an error which is epsilon, so then we can use a Taylor expansion to say something about the kind of error we're making here. Then this leads to a mean square error here between the true value and the one we're getting from our estimate. That looks like this here involving the derivatives of our conduction model here and the expected value of these epsilons here. And these epsilons, if we assume that we use the maximum likelihood estimator, then for a sufficiently high number of samples, then we know actually that these will be normally distributed and their covariance matrix will be given by the inverse of the Fisher information matrix. So, and the Fisher information matrix, if we assume that we're dealing with Gaussian signals, can be shown to have this form here. So actually, we can say something about the quality at which we can reconstruct signals, depending on the conditions we're observing our signals. Okay, so how can we estimate parameters in practice? Well, a commonly used method is maximum likelihood estimation, where you say that you form the so-called likelihood function here, P of X theta here, which looks like this. If you then say that you have, we call these snapshots here, if you have multiple of these, well then you can write the likelihood for the collection of snapshots as a product of the individual likelihoods here. And then often you take the logarithm of this here, like that, and then you find as your maximum likelihood estimate the values of theta here that maximize this function. Now, this looks, of course, pretty straightforward when you look at it here. The problem is when you have multiple parameters here and those parameters are nonlinear, because then you have complicated nonlinear estimation problems. And actually, many of the problems we keep struggling with are the nonlinear ones. So the ones we're really interested in. Okay, let's see if we can simplify this a bit. Well, if we assume that the noise is line and Gaussian, then we have that the covariance matrix here is Q is equal to a scale events matrix here. And then we can express the likelihood function here, and that's much simpler here. So if we want to maximize this, we should minimize the 2 norm of the observation minus the model over here. We can see that. And then if we concentrate this maximum likelihood estimator here, so we maximize this over the parameters, we see that we should simply try out different fundamental frequencies here, which are in the set matrix here, and then we should project our signal onto that matrix. And then the one that captures the most of the signal entity is our estimate, 0 here. And then if you use some asymptotic approximation on this inner product between the matrices here, namely the asymptotic orthogonality of complex exponential functions, then you end up with a really simple expression down here which says that you should maximize over the fundamental frequency this quantity in here, which is added up over L. And what is this? Well, if you check this out, you can see that this is actually just a Fourier transform of X evaluated at the fundamental frequency times L here. So basically, you should measure the power in the spectrum at where the harmonics would be under a certain for a certain candidate fundamental frequency, and you add that up, and then when you get the most energy, you have your estimate. Really simple. And so you can actually implement this really fast. And this is actually one of the oldest fundamental frequency estimators named called harmonic summation. And its history goes back to '69, a paper by Peter Knoll there. Only he didn't realize at the time that what he was doing was actually maximum likelihood estimation. And for a long time, this method kind of was forgotten about. And I think the reason was that when Peter Knoll invented this method, the tools for determining the model order L here were not well developed. Those didn't appear until the 70s. Kike information criterion, description length, and all those methods. At least, well, that's speculation on my part. But, I think that's the reason. But then you can actually see that these kind of methods started reappearing in recent years. Okay, but we can do this in other ways. If you recall that the model looked like this up here, and the convergence metric we could express like this, the conditions mentioned before, then this had rank L, and P contained the power of the sinusoids in the set matrix here. Then if you compute the eigenvalue decomposition of R, and so it's a U, not the U here, then you take the eigenvectors corresponding to the M minus L smallest eigenvalue, and then you stuff them in this D matrix here. Then you can show that this set matrix here should be orthogonal to the G matrix. And then, well, you might wonder how exactly is that supposed to be useful? Well, you can always compute the convergence matrix of the observed signal R here, and you can compute the eigenvalue decomposition for that, which means you can find the G here, and then you can start looking for the fundamental frequencies that generate a set matrix that's orthogonal to G. And you can formalize this concept by saying that you want to measure the angles between subspaces. The problem here is essentially how do you measure angles in multidimensional spaces, and that's not trivial by any means. But one way you can do it is actually with this Frobenius norm down here, and again you end up with something that's so simple that you can actually compute it with FFTs, because this kind of expression is similar to the harmonic summation we had before. Yes, and this actually maximizes the angle between the two subspaces formed by the column space of set and G. We can also go differently about this problem. We can say, well, we'd like to filter our observed signal here to form Y by a filter having impulse response H here, and we can write that in matrix notation like that. And we can then also see that the output power of the filter is given by H, emission transpose times R times H. Then if we apply the filter to our model, we get something like this, and from this we can make some observations. So first of all, we'd like to eliminate noise down here. So we would like to make this as small as possible in some sense. But what about this part here? Well, with this part, if we could actually make it such that this product here is 1, and a bunch of 1s, then this part would actually give us as output here the sinusoids. And that would mean that the voice speech would actually pass undistorted. So we could say here we'd like to minimize the output power subject to the constraint that the filter should give a 1 for all these sinusoids. And this you can show has this solution here. And then how we can use this for finding fundamental frequency is like this. The output power is given by this expression. We try out different fundamental frequencies and measure the output power and then choose the one that maximizes it. All right, let's look at some problems here. So let's look at multi-channel modeling first. So a myriad of different pitch estimators exist, but very few have been proposed for multiple channels. And those that have been very heuristic in nature. So what I'm doing now is I'll derive a multi-channel pitch estimator based on the parametric model. And this estimator here is quite general and makes some quite vague assumptions. And that means that you can have, we don't make any assumptions about certain array geometry or the noise power being the same in all the channels or the amplitude being the same in all the powers. So it means you can have different noise levels in different channels picked up by different microphones. You can have different microphone characteristics and all that. It doesn't matter. So this estimator here is quite general. Again, it operates on snapshots like before of the signal. Now we just have a subscript K, which means that we're looking at the Kth channel. And then for each of these channels, we model the signal as a sum of sinusoids and Gaussian noise with covariance QK here. We use the same model as before. Now we just have different amplitude vector per channel, so it's called AK. The likelihood looks like it did before. We just have all these subscript Ks now. And then if you integrate this across all combine this across all different channels and across snapshots, you get across channels, you get this expression here. And you can simplify this again by assuming that the noise is white, but that it has different noise variances. So that QK here is the variance of the noise in the cave channel times the density variance here. And then you get a simpler expression here for the likelihood function here across all the channels. For one channel, we can actually find the amplitudes that correspond to that channel. We can do that using this expression here. And we can use that to come up with an estimate of the noise variance. If you go back here, you see that it needs the noise variance here and noise variance here. We need to find those. So we can take the amplitude and plug them in here. And then for different pendant formats and frequencies here, we can subtract out the model that gives us an estimate here of the noise. And we average across the channels and snapshots. And then we get something which is really simple for log likelihood function for channel K in this expression here. So it just involves log to this variance estimate here. For all channels and all snapshots, this yields this thing here. So we simply have something that's, well, that's a constant term, so we don't care about that. But we have something here which is the sum of the log to the noise variance estimate per channel. So the maximum likelihood estimator here is the one that minimizes log to the noise variance estimate here. And this is a bit different from what you can see people have done in literature, because you would see something like that. It's a sum over the variances, for example, across the channels. But that's not correct if you assume that the noise levels are different in the different channels, as you can see here. And again, you can use the same approximation as before and simplify this expression here, which can be computed using FFTs as with the harmonic summation. You just use an FFT per channel, and you have a really simple multi-channel pitch estimate here. Okay, some results here. What you see here is something called gross error rate. So big errors in the pitch estimates obtained here under two conditions. One is called symmetrical noise level, so the same noise level in all channels. And then when you have different noise level in all channels. Now this MPF method here is one that appeared in the literature. You see here it doesn't do so well. It has a lot of errors here when we have noise. You can see that the harmonic summation here and this new max likelihood estimator, they do the same here when the noise level is the same. That's not surprising, because when the noise level is the same, then the harmonic summation is the same as that method. But when you change the noise level in the different channels, you see the picture change here. The harmonic summation method starts doing way worse, but the one based on the principles here still performs quite nicely. So you see, in a really simple way here, you could actually gain an estimator that's more robust to noise. Okay. Let's look at noise reduction. So the harmonic signal model has been used in many different ways for noise reduction. Many of you probably know about the traditional cone filter, which has been around for many, many years. But we've seen now that we can actually design adaptive and optimal comb-like filters that can be used for pitch estimation. And that principle can also be used for noise reduction. And as you'll see, we get something interesting out of that. And it also reduced to some really interesting special cases. Okay, so we saw that when we apply a filter to our observed signal here and plug in our model, we can understand what's going on. We try to estimate the speed sample as hat of n here. There are two parts: the filtered voice speech here and the filtered noise. Again, if we can design a filter such that we get ones out of this here, then we can see that what we get out of this is just the sum of sinusoids, which is exactly what we wanted. But it means that such a filter would pass pass the harmonics without adding any distortion. And well, you may think that's not a big deal, but if you look at something like the most used noise reduction filters, such as the Wiener filter, those actually distort the desired signal. And if you talk to people in the hearing aid industry, there's concern about this because obviously you cannot know if you're actually ruining the speech signal and the intelligibility of the speech signal. So if you can design filters that are guaranteed to not ruin the signal, then that's of a huge interest. Then, while having this kind of constraint here, we would also like that the output power of the part here that corresponds to the noise is minimized. So that's the filter coefficient, emission transpose times Q times H, where Q is the noise parametric. And if we minimize this, while we have this constraint, we actually have optimal distortionless noise reduction. And again, well actually the optimization, it has the same form as before, but now we have the covariance matrix in here of the noise. We'd like to minimize that, and we'd like to guarantee that the harmonics pass undistorted. And it has this solution here, and in this case, this Q here is a particular noise covariance matrix estimate. I'll return to that in a second. So what are these filters? These are adaptive optimal cone filters, and they are unlike the normally used linear filter, distortionless. And they provide the optimal output SNR 2. Yeah. So what about this Q matrix here? Well, that's an interesting thing, because in a lot of enhancement problems, a huge issue is that you need to find the statistics of the noise before you can design optimal filters. And tons of research has been devoted to that question over the past 15 years. So there's an interesting sort of aside to this whole thing here, which is that we can actually find the noise covariance matrix in the process. And the way it works is this, I'll just explain this briefly without going into too many details. But the mean square error between the output of the filter and the model of the signal here, we would like to have that minimized. What does that mean? It means we'd like to have a filter whose output resembles the sum of the sinusoids. You can put that into matrix vector notation like this here with filter, observed signal, amplitude, complex amplitude, and then there's W here with the sinusoids. And if you solve for the amplitude up here and you plug the whole thing back in, you end up that the mean square error is this thing down here. And this is the covariance matrix of the observed signal. Actually, it's the sample covariance matrix of the observed signal here. And then you subtract out this thing here. And if you look at what this thing is down here, you have this W times X, and then W times W emission transpose here. You can actually see that what this does is actually it subtracts out the contribution of the candidate harmonics from the observed the sample covariance matrix here. So this means this is actually an estimate of the noise covariance matrix. Okay, some interesting things here is that in this noise covariance matrix estimate here, if you set W equal to a density matrix, then you get what you would call the usual noise covariance matrix model-based estimate. If instead of this Q here we use R, then we got what we call Capon-like filters. So the filters I was using for finding fundamental frequency earlier. If we set it to a scale identity matrix, so we assume that the noise is white, we actually end up with just the pseudo-inverse here times a bunch of ones here. So you can see that the filter we get there is closely related to least squares and projection, those sorts of things. And if we use the asymptotic orthogonality of the sinusoids, we end up with something where here, where we basically just have the Fourier basis as our filter. So the Fourier basis is actually an optimal filter in this sense here for very long windows and white noise. And you can also explain something called binary masking using these filters. You can cast that in this framework here too, and put that on firmer ground. Let me show you an example. So we have some piece of voice speech here. We estimate the fundamental frequency, gives us this track here. If we take and use that fundamental frequency to design these filters, like I just explained, we extract this signal here, and then this is the part of the signal that was not captured by the model. So you see it captures most of the signal, but there's still something left that it didn't capture. We can also use it for separating speech signals. We take two different speech signals here, we add them to get this signal here. We estimate the fundamental frequencies here, so see one is about 200, the other is about 160 here. We apply the filters for those frequencies, and we get these estimates. So the last of the topics I'd like to talk about here is how to deal with non-stationary speech. So while we have shown time and time again that the the methods based on the harmonic model overcome a lot of the problems of the traditionally non-parametric methods, such as the articulation-based pitch estimation methods, people still say that, well, speech is not stationary and so forth. And what I'd like to look into here is that, can we take that into account and then use that as a, well, if we can, then investigate, does it make a difference? Right? If we can, then that's great. If it doesn't make a difference, then we know that from now on. So now the model will be modified a bit. So our observed signal x here looks a bit like before, but now instead of the simple model we had before, we now have what is called as an instantaneous phase up here. And that model there is going to be different than what we had before. Another thing that's different is that the indices, time indices here, will start at n0. We'll still have n samples, but they'll start at n0. And this is one of these things where you think, how on earth can this matter? How can it matter if I start counting from 0 up to n minus 1, or from minus something up to plus something? But with these methods, you can actually determine that from a strong low bound. It does make a difference. So if you choose your index wisely, you can get better estimates. In many ways, this is counterintuitive, but it's the math doesn't like it. Okay, so the instantaneous phase of the L harmonic here is the integral of L times the fundamental frequency here, and then you take the integral of that and you add a phase to that. If we differentiate this, we see that we get that the frequency of the L harmonic is simply L times the fundamental frequency, which is what we want. Often in pitch estimation, you assume that the pitch is constant for like 30, 20 milliseconds. So you're essentially saying that this does not vary with t here, pitch does L times omega 0. So you're saying it's changing from this level to that level and then down to this level again, which I think everybody agrees is not the case. But this is what gives you the harmonic model or H. If the pitch is slowly and smoothly varying, then an appropriate model would be that this kind of linear model of the fundamental frequency. So we say that there's a fundamental frequency, and then the fundamental frequency changes with alpha 0 times t as time progresses. And then this yields this instantaneous phase model here, which is a second order polynomial model. And then this alpha is what we call the fundamental chirp rate. And this model we call the harmonic chirp model. What we like to do is jointly estimate alpha 0 and omega 0 from x of n. And then we want to see if the pitch estimates we get from this are better than the ones we got with the harmonic model. Okay, so we define a vector as before, where we put our observed signal starting at n0 up to 0 plus n minus 1. We change the definition of the set matrix because the model is more complicated now. It now has two parameters, namely omega 0 and alpha 0 here, and then you multiply those by the harmonic numbers. So you see that these vectors now are no longer Fourier-like vectors, they are chirp vectors. And then we define a projection matrix like this for the set matrix here, which depends on the fundamental frequency and the chirp rate. We could, of course, apply the nonlinear least squares estimator to find this, so we simply minimize the modeling error over these parameters like that. But that's a two-dimensional nonlinear optimization problem, and it's not so easy to solve, actually. But if you observe that the chirp rate is going to be small, then you can initialize an iterative estimation procedure where you start out finding the fundamental frequency with a fundamental chirp rate of 0, and then once you find the fundamental frequency, you find a new chirp rate, and then you can find the fundamental frequency, and then back and forth like that. So that's basically what's described here. First, you find the chirp rate given the fundamental frequency, and then you find the fundamental frequency given the chirp rate. So does this matter with the model? Well, here are the spectra of just 5 harmonics for the harmonic model. That's the blue one. You can see the nice regular spectra you get there. Then if you look at the spectrum of the chirp model here, you'll see that the higher harmonics here are actually really distorted. So if you're thinking about capturing the essence of speech signals, then, and the chirp rate here is not that great, by the way. So you can see even then it causes a lot of changes to how the spectrum looks. The red one in here is a model that a lot of people have been using for these kind of things here. And this is just to show that this red one is actually not a good model of the green one. Okay, so what you see here are histograms of the differences in fundamental frequency with the harmonic model and with the chirp model. And you can see most of the time when the speech is fairly stationary, it doesn't matter so much whether you have the more sophisticated model. But on the other hand, you can see that there's a lot of times when you get differences that are up to a few hertz. And if you look up in a psychoacoustics book, this would absolutely be audible for a lot of frequencies if you used it to synthesize signals. So yeah, it does appear to make a difference there. And here you can see also differences if you reconstruct the signal with the two different models, that most of the time the difference is quite small as we'd expect, but there are times when it makes a big difference. But the main message, it's not here that we should actually use the chirp model. The main message is here is more the methodology in investigating whether it matters, right? Now we have an estimator for finding the fun. We have a modified model, we have an estimator for it, and we can investigate if it makes a difference, and if we think this difference is big enough, well, we can use these more sophisticated tools. Okay, let me wrap up here. So we have seen how the problem of finding parameters of the harmonic model can be analyzed. We've seen how the parameters of the harmonic model can be found in various ways. The harmonic model and its estimators can be extended to multiple channels under quite general conditions. We've seen that. We've also seen how we can use the harmonic model for noise reduction purposes, which is a thing, by the way, that we discovered, and that this results in filters where you actually don't need to find the noise correction. We've also seen how it's actually fairly straightforward to take the non-stationary nature of speech into account. So it is actually possible to deal with these issues. Some other problems that I'm not going into details about them here, but this problem with estimating the model order, well, you can solve that in several different ways, something that we've worked on quite a lot. So that can be solved. You can also choose between different models, again, using statistical principles. So you can even ask the question, which is a better explanation for the observed signal? Is it the chirp model, or is it the harmonic model? Or is it just a noise model? You can solve that consistently within these types of methods here. So what about the colored noise? I kept saying that the noise is white and blah, blah, blah. I don't believe the noise is white. It's not. But we can apply pre-whitening, so pre-filtering of the signal, if we can find the noise phosphorus density or covariance matrix. What if we have some missing data? What if some data is lost in transmission, like it is over the internet? What if some parts are corrupted? Well, we can deal with that also with the harmonic model. We've also shown that. You can also find an optimal segmentation of a given signal, given a set of different models. You can also solve the detection problem consistently. These ideas they can be used in many different applications. Those include hearing aids, for example, voice over IP. Many of you probably don't know this, but for a long time, a big part of Skype's research group in Stockholm was actually people from Aalborg University, and it was all headed by Søren Andersen, who's still here. We worked on some of these ideas many years ago. The ideas can be used in telecommunication. They can be used in reproduction systems. Maybe you read about some of these fancy new systems coming out these years that are able to calibrate themselves and so forth. We are also now applying some of these ideas to voice analysis, in particular to the problem of diagnosing Parkinson's from voice signals. You can also use these things for sinister things like intelligence purposes, law enforcement, defense, whatever you want to call it. And you can do more fun and interesting things with it in music equipment and software, stuff like that. So many different ways you can use these ideas. Some other results that I'd like to briefly mention here. We've also shown that parametric models can be used for speech and audio compression. We've shown how these models can be used to improve what is known as feedback cancellation. So feedback cancellation is used in basically any communication system where you probably encountered with cell phones and Skype and all that. You get echoes from the far end, and you use feedback cancellation to avoid that. And if you use these models, you can do this better than with traditional methods. You can do better beamforming when you have microphone arrays with the model-based approach. And an interesting thing is that we found out quite recently is that these optimal filters I talked about here can also be designed for the chirp model. And that's interesting because it means you can actually design optimal filters that take the non-stationary nature of speech into account. And that's not something you can really find out there with the possible exception of Kalman filters. So I think that's a bit remarkable. You can also do model-based time difference of arrival estimation if you have multiple sensors with the model. And something we also worked on is that you can also model how stereo signals are generated in studios and take that into account to get better transcription methods for music. And something that I also like to highlight is that we also recently showed that how you can actually implement these things fast, because that was like one of the last arguments people had against these methods. That it's like, yeah, you come up with all your fancy methods, you take all this into account, that into account, but it's really slow. And then, well, that was thanks to Jesper and Tobias that we finally were able to do that. Okay, so conclusion. Parametric models have shown promise for several problems, but they're not yet widespread. And an argument against the usage of these models is that they do not take various phenomena into account. And the thing I keep stressing again and again is that we can only have this discussion because the assumptions are explicit. And as you've seen here, it's actually fairly easy to improve the model and the methods if we need to. And this is because the parametric methods lead to mathematically tractable methods. And I think there are many, many more speech and audio processing problems that could benefit from this approach. And some of them are the ones where you have multiple channels, where you have really adverse, noisy conditions, and the applications where the really fine details of the signals matter, where you like to get the best possible estimates. So, finally, there are some people I think I should thank here. So first of all, the elders, John Jensen, and then Jonathan, Steve, Mahmoud, and Stoika, the young guns, some of which are here today. Jesper, and I could have put another Jesper in there, but I didn't. Daniel and Tobias, my current and recent PhD students, Sam, Sissel, Vincent, Martin, Knut, Matthew, and Charlotte. And finally, my family, Nia, Silke, Fire, and last but not least, Eric. Thank you. Questions? Or?
Yeah, thank you very much for your speak. I'd like to, if you have time for some questions from the audience. Yes, yeah.
Of course, Jan has a question.
so Mads, these wonderful parametric sinusoidal harmonic models, are they the universal cure for everything, or do we need something else?
They do not explain everything, of course, and I know what your background is, of course, and I think a lot of the traditional signal processing methods can also benefit from a lot of the kind of models that we use in machine learning, and somehow thinking how can you incorporate that knowledge in this kind of framework, like the optimal filtering framework, and then do some of the same things. Absolutely. And I think also the more knowledge you can incorporate about the signals you're dealing with and the problems you can in your algorithms, the better. And so for example, here there's no model of the speech spectrum, for example, which is something you could fairly easily do. Right? There's no model of the temporal development of things. There's no language model or anything like that. And for sure, that stuff will only make things better. I think one thing we've changed a bit in how we looked at it was this basic question of should you actually use the models themselves for resynthesizing signals. So you might wonder, should you use the model to, like in a noise reduction scenario, why, if you found the parameters, why don't you use those parameters to resynthesize the signal? And if you look at what goes on in source separation there, what people use the models for is not to generate a reconstructed signal. It's for finding the filters that should be applied to the observed signal to extract the signal. And I think we're moving probably a bit in that direction there too, because it's really hard to capture everything in these models. And no matter what you do, there's always some part of it that you miss. And apparently this approach of deriving filters from the models rather than using the models themselves is more robust towards the errors that you make. I do think that the parametric methods do give a really good handle on a lot of problems. And I think if you look at the music information retrieval community, they of course use a lot of machine learning methods for things like transcription. But if you look at something like pitch estimation, it's really a continuous, pitch is a continuous phenomenon, right? It's not a discrete one. And that makes it, modeling a problem like that with something like non-negative matrix factorization tremendously difficult, I would say, with these more discrete type methods. But to me, it's not one or the other, right? It's different ideas that are basically complementary. That's how I see it. So you can keep on doing your thing and I'll do my thing.
Thank you.
Are there even more questions? Yes?
I wonder why do you need pitch estimation for speech processing?
Oh, but pitch is used for many, many different things here, or it can be used for many, many different things. It is used in every time you use your cell phone for communicating. It's used there in the form of a long-term predictor, usually for coding efficiency. In some languages, pitch carries semantic information. For example, in Chinese, I believe, it carries semantic information. So if you're building speech recognition systems, then pitch is part of the picture there. And like I said, even if you don't use the pitch itself, it gives you a handle on a lot of problems, and you can use them all for doing many, many things, as you've seen, like noise reduction, feedback cancellation, or what have you. So many, many, many different things. Also, a comment more, actually. If you look at, you could say that my approach is based on like physics and math. And if you look at the other end of the spectrum of people who work on these sorts of things, there you have what is known as the computational auditory scene analysis people, who who claim to be taking their starting point in how the human auditory system works. And they say that basically there's a bunch of features that are the ones that the auditory system locks onto when it tries to separate speech signals and track them and move around and all that, talk at the same time and all that. So one is location, so direction. Another is timbre, so that's spectrum, for example, or temporal envelope also. And the last one is pitch. So you could say that there's also a strong indication there that the human auditory system also exploits this information. And I would say that it makes sense that it does, because the pitch is a very strong cue that can be found in very adverse conditions. And let me elaborate what I mean by this. If you try to find the individual harmonics of voice speech under noisy conditions, then finding the parameters of those is more difficult than finding the pitch. So by using the knowledge of the structure of the signal, you can actually do better than trying to look for the individual parts. So I would say from an evolutionary point of view, it makes perfect sense. Jan, you had a question?
Yeah, it was when it ended a bit so that you said the mean squared error was absolute, so you made a fix for it. I was just wondering whether you made some other metrics instead of the mean squared error.
Oh, can of worms, huh? Yeah. So there are a lot of people now interested in speech intelligibility. Right? So you and I come from an audio coding background, so we were interested in quality. And in like the hearing aid companies, they realized that quality is not necessarily the same as intelligibility. So there's so much research now devoted to coming up with measures of intelligibility, which is tremendously difficult. We have not contributed to any such measure, but we have looked into how you can possibly use them. But I'm not sure how much I can talk about that stuff. But that's definitely a very interesting subject. I think also if you look at the noise reduction methods I talked about there, you had one part which is about suppressing noise, and you had another part which is about preserving the characteristics of the speech. And I think it's quite recently that people in the community have started thinking about these two things, and that there's an inherent trade-off between them. You know, if you insist that you won't ruin the speech signal, then maybe you cannot remove all the noise you need to remove. Right? Or you try to remove the noise because you think that's a good idea, but you end up harming the speech signal. And I think also perceptually, speech distortion and additive noise, those are two different things that probably should be addressed in different ways. And I haven't seen any research addressing those sorts of issues. But I suppose that's maybe a question for Torsten Dahl or somebody like that. Anything else?
Good. Good. Så should be masser af